So what we do now is reconvene to do learning outcomes 3 and 4, which will be tested, assessed in paper 2 examination in May. So learning outcome 3 says you're going to need to be able to use Fourier series calculation techniques as a means of analysing circuits involving complex waveforms. Okay, that's assessed in exam paper 2, so it'll be assessed with one of the, I would think that'll be 2 questions again for the 1 hour exam paper, and there'll be one on complex waveforms. So we're going to study this over the next 4 or 5 weeks, and then the other learning outcome on Laplace transforms will be the other 4 or 5 weeks, and then we'll have some revision at the end. Okay, so what we're going to look at today is what are complex waveforms, look at the calculation of current for a circuit supplied by a complex waveform. This is over all the weeks, by the way, not just today. Fourier series calculations to find components of common waveforms. Resonance and the issues caused by resonance with undesired resonance with harmonic frequencies, which will become a bit clearer once you're fully aware of what a harmonic frequency means. Okay? So, first of all, a complex waveform, a repetitive complex wave of fundamental or base frequency f, can be resolved into the sum of a number of sinusoidal waveforms having frequencies of f, 2f, 3f and so on. So multiples of the base frequency f can be added, and we have then the complex waveform. The component parts of the complex waves are called harmonics, with the second harmonic, so the base frequency is called the fundamental, and the waveform repeats for every cycle of the fundamental, and then the second harmonic is twice of that frequency, the third harmonic 3 times, and so on. So for a 50 Hertz main sine wave being the fundamental, the second harmonic would be 100 Hertz, third harmonic 150, and so on like that. It can be shown that the equation for a sine wave is, and you should be reasonably familiar with that, point out that it is little v at time t. So it's the instantaneous value of voltage, a sine wave, is the big V stands for the maximum or amplitude of that waveform. So the maximum value, sine omega t. Omega is the angular velocity in radians per second, and it comes from the calculation 2 pi times f. Okay? So we're going to be looking at the way we can add several of those together with different frequencies into a complex waveform, and then considering what that means for a circuit that's being supplied by complex waveform, maybe intentionally, maybe unintentionally, unwanted harmonics. So we can have a general equation for a complex wave can be along these lines. V little t is equal to V1, the amplitude of sine omega t, that would be the fundamental, plus V2, a different amplitude. So each of these components can have, and usually do have, different amplitudes. They're usually getting smaller and smaller as you go along the line here. Amplitude of the second harmonic, 2 times omega, means double the frequency. Amplitude of the third harmonic, 3 times the frequency, and so on. If the sine wave contained, or a complex wave, contained a DC component, then that would go on at the beginning as a simple addition. All that's going to do is move the whole waveform up and down the Y scale. So if we take a base sine wave, like so, add in a DC component, would lift that up the y-axis, taking away a DC component would move it down the y-axis. Okay, so depending on what the waveform shape is like, it may or may not have a DC component at the beginning with no sine wave term. So here again, DC component, fundamental, second harmonic, third harmonic, and that can carry on for as long as you want. Okay, everybody reasonably happy with that? So, if we look at that graphically, and we consider combining the fundamental with odd harmonics. So this first diagram here, first graph is 100 sine omega t, and this one is 100 over 3, so it's a third of the amplitude of the fundamental, and 3 times the frequency. So in one period of the fundamental, which is pi, we're actually getting 1, 2, 3 full waveforms of the third harmonic. Adding those two together, which is what we're doing here, we end up with a waveform that looks like that. So here you can kind of see the fundamental in that, and then this one sitting on top of it and on the bottom of it. Yeah. Okay, so it's a waveform with two components, fundamental of 100 volts peak amplitude and a third harmonic of 30, I'll put 30, but I'll add about 33, a third of two waves. These two waveforms are in phase. There's no phase difference between the fundamental and the harmonic. But you can consider waveforms where there are phase differences as well. If we add a fifth harmonic, so 100 over 5, and again we're reducing the amplitude by the number of the harmonic. So we've gone third harmonic is 100 over 3, fifth harmonic is 100 over 5. This is the result. So we've added those two together, we get that. What we could note there is there's a tendency for the resultant waveform to move towards a square wave shape. If we added a seventh harmonic on there, we'd end up even closer to what looked like a square wave, and the ripple top and bottom would gradually get smaller and smaller as we added more and more odd harmonics. And in actual fact, if you consider an infinite number of odd harmonics being added on, you'd have a perfect square wave. Okay? Generally, we'd probably only need, for what we're going to do, to consider what it's like up to about the fifth or sixth harmonic anyway, because the magnitudes of the components get so small, they're not necessarily so much of an issue to us with regards to resonance in the circuits. We're going to consider it being expressed as a Fourier series a bit later on, okay? But what we're going to now have a look at is calculations involving complex waveforms. So, when a complex alternating current voltage is applied to for instance, a single phase circuit, containing R, L and or C components, so resistance, inductance, capacitive components. So you're going to be stepping back a little bit here and start to move back into a little bit of our complex numbers and calculating impedance in our RL, RC and RLC circuits that we done earlier. The resultant current will also be complex and contain harmonics as well. So the current will have those same harmonic components, but not necessarily be in phase with the voltage. As stated before, the component parts of the complex wave could be considered to be quite separate. So what we can do is calculate the circuit conditions for each of those 3 or 4 harmonic frequencies and amplitudes and add the results together to get an overall result. It's a bit like superposition, really. It's like having 3 sources in the circuit all added together. You consider each one separately and then perhaps what they combine together to make as well. Okay? So you can find the impedance at the fundamental frequency, the impedance at the 3rd harmonic, the 5th harmonic. That's going to be different because the impedance of the X and XL and XC components changes with frequency, remember. Yeah? So, we'll have a look at this one together. We've got a complex voltage containing a fundamental and 2 harmonic components. This is a 300, we've got 100 pi t fundamental, 300 pi t, so that must be the 3rd harmonic, and a 500 pi t 5th harmonic added together. Yep. Supplying this circuit with that 12 ohm resistor, 9.55 millihenry inductor. We want to calculate an expression for the current. So effectively we want an expression for little I at time t. Okay. What we can do is calculate the current for each component. Separately. That's how we would do it. Okay, so I've given you several slides so we can put the calculations for each bit on a separate page. So first of all, find the fundamental current. So we've got fundamental is 240 volts at sine 100 pi t. Okay, how can we go about finding this current here in that circuit? Formula for current. Yep. So we'll call it, for the fundamental, we'll call it Z1. Yep. This is going to be I1, the current due to the fundamental frequency. Formula for impedance in this type of circuit. R, yeah. Bit missing. Yep. So is there something we need to calculate first? Yeah. XL is equal to, yeah, but we haven't got the frequency in F, we've got it in omega. So we can just go omega L. Yeah? So 100 pi times 9.55 times 10 to the minus 3. Someone push the buttons. Yeah. Therefore, Z1 is equal to 12, the resistance, plus 3 J ohms. Convert that to polar, please. Yeah, 12.4 plus 0.245 radians. Okay. And then we calculate now the current. V1 over Z1. V1 was 240. Angle. Right, so we haven't divided the voltage V1 by the impedance, we end up with a fundamental current of 19.4 amps at angle minus 0.245 radians. Yeah, this gives us the first part of our I at T. The first component of that is going to be 19.4 peak amplitude, yeah, sine 100 pi t, same frequency as the voltage, yeah, but minus 0.245 radians for the phase difference between voltage and current. Yep. Everyone happy with that? So now we want to consider the current due to the third harmonic. So following the same process as we did before, 5-10 minutes, see if you can come up with an expression to add to that to make the addition of the third harmonic current. So you've got to calculate a new XL, a new overall impedance that you can divide by that divide into that voltage to get a second component to the current.